Okay, I think we're down to our last four classes before the final. That is, I am very excited. I'm still trying to get over this weird cough thing I've got. I feel completely fine, but I'm having trouble still talking, so see how this goes. We're going to not follow the schedule for today. We're actually going to, this is on our schedule, but it's supposed to be in a few days. We're going to do this one today, this section, and then we're going to do a different type of integration next class, and then next week is just going to be applications. So just so you know, I'm changing the order a little bit. All right, so we're going to do this thing called integration by substitution. So I need to kind of get you thinking about this. So what I want to do is start with an example. Let's say we have y equals, let's go 3x plus 1 raised to the 4th power, and we're asked to find the derivative of this. So this is not new. We've done this already, but let's just try and remember what we need to do here. To do this, we had to use the chain rule. All right, so we had to realize that we have, something that's being raised to the 4th power. So that 4 will drop out first. All right, so our derivative here would be 4. And then what? The 3x plus 1, we just rewrite it, right? We don't take the derivative. And then what power on that 3x plus 1? 3. And then am I done? No. Then what do I have to do? Take the derivative of what's here, right? And the derivative of the inside piece there is 3. Yes? Okay, so if we put the 3 times the 4, the final result here would be 12 times 3x plus 1 to the 3rd power, and we would box that, and we'd be done, right? That's how we would take the derivative of this. The question today is, how do we go backwards, right? From this back to this, right? And to do it, that means take the antiderivative. And we have not dealt with anything like this. What we've been able to do so far is we can take the antiderivative of x to a power. We have a formula for this, in fact. We did this in class. It was 1 over n plus 1, x to the n plus 1, and then we always threw that c out there. So in other words, if we had x to a power, we would just add 1 to the power, then we would put out in front of it 1 over whatever that power was plus 1. Have we done enough of those that y'all feel okay with that? Yes? We also know that the antiderivative of 1 over x was natural log of x plus c. So this was that special case when n was -1. We did that. And then there was another one we've done. Antiderivative of e to the x is what? Just itself, right? E to the x plus some constant. So these are the ones that we've done, all right? None of these required any real additional work. It was just understanding the formula. So if we're looking at this problem right here, so let's say I started this out and I said, hey everyone, I would like us to find the antiderivative of 12 times 3x plus 1 to the 3rd power. How do we get that back to what we know the answer should be? The answer should be that, right? This was what we took the derivative of earlier. And then we would have to say plus c. But how do we get to this from that? So how do we do that? Well, it doesn't look like this, right? We don't have just x's to powers, right? Because of this cubed up here, this is not, we can't just look at the 3x by itself and do that rule, right? We can't do that because of the cubed. So what is the process to go backwards? And this is where this idea of substitution comes from. It's very different. It's probably going to be one of the more difficult things we do, all right? We'll see how it goes with you, all right? Do you all understand what we're trying to do, though? Yeah. Yes? Okay. So here's the process for substitution. It's going to look It's going to look really weird. It's going to sound very strange until I start to do some examples, and then hopefully you'll start to catch on. All right? All right, so for substitution, here's the technique that we're going to use. First of all, find something and its derivative. I know this sounds weird, but all right. What am I talking about? Find something and its derivative. So what you need to do is you need to look at this over here, and you need to see if you can see something in the problem, and at the same time, somewhere else in the problem, see its derivative. What? Okay, so let me try and start this out. I'm going to try and see if I can find something in here. How about this right here? How about 3x plus 1? You see that right there? What is the derivative of 3x plus 1? 3. So I said to try and find something, right? And the something that I just found is this red piece. I need to also see its derivative in here somewhere. You said the derivative of 3x plus 1 was what?
3.
3. Do you see a 3 in here? Where? Well, the power 3, yes, I agree, but that's a power 3. Do we see the number 3, like 3 being multiplied by something? Where? Where? This is 4 times 3. 12 is 4 times 3, isn't it? Yes? So let me just kind of rewrite the problem for a second. This is 4 times 3 times 3x plus 1 cubed dx. So again, do we see something? Yes, I see something here. And do I see its derivative? Yes, there's its derivative. See what I'm saying? You sure? Now we had to break that 12 up to see it, right? But it's there. There's the 3. So here's what we're going to do. If we can find something, are there any questions? Because if you don't see this part, then it's going to be difficult. We're all good? Okay. So now what we're going to do is this. We're going to make what we call a substitution. We are going to let u be equal to the something. Whatever it is that we found, we are going to call it u now. So let's do that over here. On the side here, on the side separate from this, I'm going to make a substitution. I'm going to let u be equal to what? 3x plus 1. All right? That's what I'm going to do. Once I do that, the next step is to find u prime, which is the same as du dx. In other words, do you remember when we wrote y prime on the board a long time ago? And we said this is the same as dy dx? Well, if I write u prime on the board, that's the same as du dx. Okay, so we're just using u instead of y. So now, this is step 3, sorry. So now what I'm going to do is I'm going to take the derivative of that substitution. So let me do that right here. Du dx, that's the derivative here, is equal to, what did we say the derivative of this was? 3, right? Okay. Is that all right with you? I'm going to do one more additional thing here. And you tell me what I did. What did I do to get from that second line to the third line? I just basically multiplied dx on both sides. So is that fair? We got this? All right. Fourth step. Rewrite the integral in terms of u. What I mean by this is we're going to come back to the original problem here, and we're going to rewrite it where we don't have x's anymore. Instead, we have u's. Does this seem like a lot of work to have to do to go backwards here? I mean, it's a lot more than just adding 1 to the power and then putting 1 over n plus 1 out front. I mean, it's a lot more than that, right? That's what makes this a little more challenging, because there's a lot going on. So I'm going to rewrite this integral, and I'm going to rewrite it where there's no more x's. I shouldn't have any x's here. This should not be an x. Everything in this new problem, in the new integral, should just have u's in it, all right? So before I do that, watch what I'm going to do. 4 3x plus 1 cubed times 3 dx. All I did is I just kind of moved things around. I moved this 3 back here to this next to the dx, and I'm going to show you why I did that. Do you see right now that I can take 3x plus 1 and replace it with u? So I can replace this right here with u, right? Then I can take 3 dx, anywhere I see 3 dx, and replace it with what? Du. So I'm going to be able to replace that with du. Do y'all see that? That's going to become that, and that is my u, right? My arrow should probably go the other way. Yes? So if I rewrite the problem right now in terms of u, this will be the integral, 4 doesn't change, that's just still there, times, now this is going to be replaced with u, right? So this will be u what? U cubed. And then what am I replacing 3 dx with? Du. Right? Now at this point, step 5, we're going to solve the integral. In other words, we're going to find the antiderivative. Okay, so on my step 6, which I'll put up here, what is the antiderivative of 4u cubed? So this is like if I would have walked in here today and I said, hey everyone, what's the antiderivative of 4x cubed dx? Then you would have said the 4 comes for the ride, right? Then you would have said I'm going to add 1 to that power, so it's going to be x to the 4th. But I'm going to have to, in front of it, put 1/4, right? That's what we would have done. We're going to do the exact same thing, except we're going to have u instead of x. Okay? So this is going to become, this right here becomes the 4 out front times the 1/4, u to the 4th, and then you say plus c. What happens with that 4 and that 1/4? This right here. They just kind of cross out, right? And all you're left with is u to the 4th plus c. And that'll bring us to our last step now, step 6. Switch back to x. What I mean by that is my original problem had x's in it, right? We made a substitution that switched it to u's. My answer right now has u in it. I want to switch back to x. So what is u? What is u? Did I erase it? Yeah, I erased it. U was 3x plus 1. So this becomes 3x plus 1 to the 4th plus c. And isn't that what I said we need to get back to? Yes. That's a lot of work, isn't it? Doesn't that seem like a lot of work? I think another example is in order. Would you agree? So this is it. In a traditional, you know how I told you a long time ago that like there's a difference between like business calculus and real calculus. Like in a real calculus class, this is the first technique that you learn on how to integrate things, substitution. And then comes integration by parts, partial fraction decomposition, trig integrals, and I'm missing something. Trigonometric substitutions. So there's a bunch of different things that you do. That's kind of what makes Cal 2 hard, Cal 1 and Cal 2 hard. But in this class, substitution, we're gonna stay very. These are still, I guess, considered basic, but compared to what we've done, this is a lot. This is a lot more than what we've done. So, all right, let's do another one. Now these steps that I gave you here, there is something here on this first step where I say find something and its derivative. I want to put a little asterisk here next to its derivative because there is something else I need to add to that, but I didn't want to add it yet because it would just confuse you. So, or confuse you more, I should say. Let's do another one. All right, how about this? Antiderivative of e to the 5x minus 4 dx. Yeah, let's do that. So you might think that the antiderivative of this is just this. That's what you might think, because I've told you the antiderivative of e is itself, right? That's true if it's e to the x. But if it's e to something other than x, like this, then it's more complicated. Just try it for yourself. If you think this is the answer, take the derivative of this. What's the derivative of e to something? Itself, right? So the derivative of this, if I ask you to take derivative, you would say it's e to the 5x minus 4. But then times, the chain rule would say, then you have to take derivative of what's up here, which would be 5, right? You don't have a 5 here. So you're off by 5. Somehow, this is not the answer. You can't go from here backwards is not this, because when we go from here to here, we get a 5 that's not up there, right? So we have to account for that somehow. We're about to do it, but there's a process for it. All right, so let's see. Do you see something in its derivative? This is, I guess, the hardest part, is trying to figure out what it is, what this something is. 5x minus 4? Okay, so let's try it. If that's going to be my u, if that's my something, what's its derivative? What's the derivative of 5x minus 4? 5. Do you see a 5 here, other than the 5 up there? You can't look at that anymore. Do you see a 5 anywhere here? No. You're off, right? By a constant? Like, it would be real nice if we had a 5 out here, right? We're off by a constant. Is that okay to be off by a constant? Well, that's why I put that star there. Because that little star, that little asterisk, is saying that when you find something and you're looking for its derivative, it's okay to be off by a constant. But that's it. You can only be off by a constant. So like, well, I'll do another example in a second to show you what I mean. But next to this little star, I want you to put, it's okay to be off by a constant. Do you know what I mean when I say that? Off by a constant? Do you get what I am saying with that? Yes? No? No? Okay. So right now, we were trying to find something, right? We were trying to find something. And the suggestion was that we let u, the something, be 5x minus 4. That was the suggestion. Let's go for this. Let's try that. Now we need to see, is its derivative here? So what is the derivative of this? So you take the derivative and you get 5, don't you? Okay, do you see a 5 somewhere in here? You can't look at that because that's already your u. So do you see a 5 here? So you're off, right? It's not, you don't have that. But it's okay to be off by a constant. When we say constant, we mean a number. Okay. So we're off by a number, right? We're off by 5. It's okay though. According to this method, it's okay to be off by a number. All right?
So just a number, not like
Just a number. It can't be off by, like, if it was an x in there also, 5x, then no. Okay, so if this said like 5x, then we would not have a 5x down here anywhere, right? That would be more than being off by a constant. Okay?
So what would you do if like it were off?
Yeah, then I gave you a bad problem that we can't do. Yeah, every problem I give you, we're going to be off by something we can handle.
Okay.
Yeah. All right. Until next class, and then there will be a way to do it. Yeah. All right, we good? So we're off by a constant. That's okay. So I let u be something. There it is. I took the derivative, right? I'm off by a constant. We're still okay. But now what I need to do is play this little game. And we did this just on the previous problem. I multiply both sides by dx, right? And in the last problem, this was 3 dx, wasn't it? And we had 3 dx in our problem. This time, we don't have 5 dx. We already knew we weren't going to have 5 dx. All we have in our problem is dx, right? We don't have 5 dx. So what I'd like for us to do here is I'd like to get that dx by itself. How could I get that dx by itself in that little equation right here? What could I do to get that dx by itself? Divide both sides by 5, right? Yes? So I'm going to write it a different way. I'm going to actually multiply both sides by 1/5, which has the same effect, right? Dividing by 5 is the same as multiplying by 1/5. So this is the same as this, right? At this point, we should be able to rewrite the integral in terms of u. Let's see if this works. This 5x minus 4 is my u. This dx right here is this, right? So just come back up to the problem and rewrite it, replacing everything with what it is over here on this little chart. So I'm going to have integral e to what power? What's 5x minus 4 for us? U, right? That's u. So it's e raised to the u times dx, but what's dx? 1/5 times du. Y'all okay with that? Dx is this. That's u, and so I've rewritten the problem. I have no more x's. Everything's in terms of u. Now I'm going to just do one more thing before I take the antiderivative. I just slid that 1/5 out to the front because it's multiplication. I'm allowed to do that, right? I'm allowed to move multiplication out. So if we were to have walked in today and I said, hey everyone, what's the antiderivative of e to the x dx? You would have said e to the x, right? Now I have e to the u du, so what's the antiderivative of e to the u? Just itself, right? So this should be 1/5 e to the u. And then always have to do this on antiderivatives, plus c. And what is the last step? We've solved the integral. Get it back in terms of x. So I'm going to rewrite this as 1/5 e to the what? 5x minus 4 plus some constant, and then box it up. Now, there's some good news. The good news is that we can check our answer. How would we check our answer to see if this is correct? Just take the derivative. And if we take the derivative of that, we better get this. So would we? If I took the derivative, this 1/5 out here, just cover it up for a second. The derivative of this would be itself, but then times 5, because remember the chain rule, we have to take derivative of what's up there. So we would have this times 5, but then times 1/5, so the 5 and the 1/5 would cancel, and you would get this. So I told you we were going to have that 5 out there, and we need to somehow undo it. The substitution is what helps us undo it. I know this seems like a lot of work for just a little tweak of 1/5 out here, but this is what it takes. I think we need to do a couple more for sure. Are there any questions though? Okay, let's try this one. I think this one is going to be a little bumpy. All right, let me start by saying there's nothing we could do to solve this problem with anything that we learned before this class, okay? There's no way you can't split this up into two fractions. You can't do that because the only way you can split this up is if you had two terms on top and one term on the bottom. Then you can split it. But it's the other way around, so you can't split this up. So we're pretty much stuck. But we also have this new technique called substitution, which doesn't always work, okay? This is just a technique. All right, I'm going to erase this. You need to find something and its derivative. Anybody see it? The bottom?
Yeah.
The denominator, x cubed plus 1, you want to let that be your u?
Yes.
Okay, let's try that. If we let u be the bottom, then what is the derivative of this thing? What? 3x squared. Do you have a 3x squared sitting there? Yes, you do. Exactly, right? There it is. You'll see it? So if we let this be the u, there's its derivative. Just so happened to be perfect, right? I'm going to do something here to help you see this a little bit better, hopefully. Do you all agree that that's the same expression? That if you have this 3x squared out here being multiplied, this is really like 3x squared over 1, and that 3x squared would just go on top. Yeah? But by me pulling it off to the side, I think this might help us write things out again when we have to replace all our x's. What was the step I did after this that I keep doing on each problem? Putting the dx over here, right? So that's going to be standard practice, okay? We are going to do that every single time. We're going to put that dx on the other side. So now we need to play a little matching game. Can we replace this? Does this appear over there? This exactly. Yes? That's it right there, right? That's it. That's going to be replaced with what? Du. Right? Now, this right here, this bottom piece is this exactly, isn't it? So that will be replaced with u. So everything looks like it's going to fit perfectly here, doesn't it? I'm going to rewrite the problem. This becomes integral. 1 is still on top, 1 over u, and then this part is du. See how everything kind of fit in perfectly here? This was du, this was u, and now we have this. What is the antiderivative of 1 over u? Natural log, right? That's, again, going back to the whole idea of if I asked you what's the antiderivative of 1 over x dx, you would say natural log of x. But because it's in terms of u, you're going to say that the antiderivative of this is natural log of u plus some constant. And then switch it back to x now. So what's the u going to be replaced with? X cubed plus 1. So I'm going to write natural log of x cubed plus 1 plus c. You do have to put the x cubed plus 1 in parentheses, because all of this is going to be plugged into the natural log function. It would be incorrect to write that. That's not right. Okay? So, no. Okay, how about this one? How about 5x to the fourth times x to the fifth plus 1 to the seventh dx? Now that's starting to look pretty nasty, huh? So when you see an antiderivative like this, the first thing that you should be thinking is, does this look like, does this look like x to a power? Because that's the power rule. That's what we learned a few classes ago. And this is an relatively easy method to use, right? Just add 1 to the power. Do you have that? Well, kind of, right? I mean, like you have x to a power here, right? But then you have multiplication. And then you have x to a power plus 1, but then to a power. So the only way that this formula works is if you have individual x's to powers separated with addition and subtraction. If you don't have that, you can't use it. But that's the first thing you want to think, is can I use this rule? If you cannot, you must move into the next technique that we have, and that technique is substitution. All right? Well, your job right now is to figure out a u. So you need to try and see something in its derivative. I know a few of you have got this, but I'm going to ask for somebody who has not responded to go for it and tell me a u. I mean, sometimes you just have to try. You just have to go for it. So does anybody see something and its derivative is also present in the problem somewhere? Anyone from this table?
5x to the fourth.
5x to the fourth. What about it? That's
Like the one like inside the parentheses, like you can. That's like the.
yes.
Yeah.
Yes, this is the derivative of this. I think that's what you're saying. X to the fifth plus 1. If we let that be our u, the derivative of this is right there. Agreed? That's what we all need to see. If we let that be u, there's its derivative. So I'm going to let u be x to the fifth plus 1. Its derivative is 5x to the fourth. And when we multiply both sides by dx, we get 5x to the fourth dx. Yeah? Okay. I'm going to take this problem and I'm going to rewrite it. All I've done here is taken the 5x to the fourth, popped it out to the back like this, and that's just to help you see where the substitution is going to be. This 5x to the fourth, right here, is this right here, right? That whole thing in purple is going to be replaced with what? du, right? du. And then this piece right here, x to the fifth plus 1, is going to be replaced with what? u, right? u. So what does this new integral become? u to the 7th, right? We still have the 7th power there. So u to the 7th times this whole thing in purple, which was just du. And now you basically have this rule. Don't you have this rule right here? You have your variable to a power, right? So you can use the power rule on that. What is the antiderivative of u to the 7th? 1 over 8, u to the 8 plus c. And the last step, replace the u with whatever it was, right? Which is this big ugly thing up there. So this is going to become 1/8 in parentheses x to the 5th plus 1 to the 8th plus c. Are y'all starting to catch on to how this works? Now, I have to pick these problems very carefully so that they work, okay? Because if I change this to like 5x cubed, this wouldn't work, all right? So we're still being very, very careful on how we present these problems to you. This will be interesting to see how you deal with this. How about this one? How does this feel to y'all? I mean, give me some feedback here. Do y'all feel, is this kind of making you a little uncomfortable, or? It's harder, but you're following it? Okay. You got to practice to get good at this. All right, what do you think? See, there's kind of, what makes this stuff so damn difficult is that you know you have to use substitution here, right? You know that because that's what we're talking about. But in general, if somebody just gives you a thing and says find the antiderivative, you don't really know what to do with it. And like I said, there's like 6 different things that we teach students to do. You're only going to learn 2 of them. But that's what makes it so hard, is there's no like cookie cutter way you do every problem. Every problem is unique, and you have to know what to do. And that only comes with practice. All right, so because you know this is substitution, let's see, we'll go with, we'll go with this table here. So we're going to force, no one else can answer. Somebody at this table has to tell me what you want to use for u.
10x minus 5.
10x minus 5. Do you see its derivative there? So let me jot it down real quick. You want me to use 10x minus 5. I don't know if this is going to work. What's the derivative of this? 10. Okay, which means this will become 10 dx, yes? Okay. So did you see a 10, but you can't count that 10. Do you see a 10 up there? Is that okay? It's okay though, right? You can be off by 10. You can be off by a constant. So this looks like a legitimate way to go. So you write down u is 10x minus 5. The derivative of that is 10. You bring the dx to the other side. And now we have to play this little matching game where we know we can replace this piece right here. That piece right there is going to get replaced with u. But what about this piece dx? What are we going to replace that with? Yeah, we can't. We have 10 dx over here, right? So we need to get the dx by itself, so we're going to multiply both sides by 1/10. Right? And that should multiply by 1/10 over here, multiply by 1/10 here, and it goes away, and we just have the dx by itself. So it's like what you're doing is you're trying to take the original problem, and you're trying to rewrite it in terms of u, But you got to know exactly what's going to be replaced with what. And if you have to tweak an equation a little bit to get it to match up exactly, then you have to tweak the equation. Everyone understand that? Okay, so let's rewrite this. Integral, what? What's this going to turn into? 1 over u? And what does dx turn into? 1/10 du, right? 1/10 du. Now, 1/10 is a constant, so don't let it freak you out. That can just kind of go out in front. And remember that when you take derivatives or antiderivatives, constants out front just come for the ride. So this 1/10 will come for the ride. What's the antiderivative of 1 over u du? ln u, right? ln u. So we're going to have 1/10 came for the ride, ln u plus c. We done? Nope. Got to replace u with 10x minus 5. I think you're ready for something else. Yes? Keep going. We're just going to do a bunch of these, but they're going to get a little harder. Let's see. How about this one? All right, table back there is up. You've answered a few times, so I think I'm going to have to cut you out. I know some of you have done integration, have done these techniques before, so I want someone who's brand new to this today, never seen this before. I want them to take that leap of faith out there and try and come up with something. Anyone at that table have something for this? This is kind of like playing the lottery. You can't win if you don't play, right? You have to play here. You might pick the wrong u, you might mess up. So far, we have not picked an incorrect u. We've been right every single time. So, what do you think? Take a swing. No, you don't need to take care of the square root. Just look in there and see. You've got to pick something to be u. All right? What can you pick? And the derivative of it has to also appear somewhere in here, but you can be off by a constant. Take a swing. 3x plus, that is correct. Now let's see why it's correct. Let's see why it's correct, though, okay? Because the sooner you see why it's correct, the easier this becomes. 3x plus 5. What is the derivative of 3x plus 5? 3, right? And if we rewrite du, it'll become 3 dx. So coming back over here, we are going to replace this with u. Yes? That's going to be our u. Now, did we have a 3 sitting here anywhere? We can't count that. Did we have a 3? No, but it's okay to be off by a constant, right? So we're worried about that. So what would I need to do next? I'm going to be able to replace this with u, but I now need to be able to replace this, right? And that's right here. Yeah, get it by itself. So what will I do to get it by itself? Yep, multiply the other side by 1/3, and now you have dx. There you go. And now we rewrite it, right? We rewrite it. This will become square root right? The square root stays here because we're not replacing the square root. So square root of what? U, that's the 3x plus 5. And then the dx became 1/3 du. So this is good so far. What about that 1/3? Do we care too much about this? No? We're just going to bring that out front. Uh-oh. How do we find the antiderivative of square root of u?
It's 1/2.
Yeah, square root of u is the same as u raised to the 1/2. Isn't it? So this is the same as 1/3 u raised to the 1/2 du. So I'm rewriting the radical as a rational exponent, and that way I can use the power rule. The power rule was that rule where you added 1 to the power, right? So we're just going to add 1 to that. We're going to have to do a number out front, so let's see what we get. This becomes 1/3, comes for the ride, and then I'm going to have 1 over what? I have to add 1 to this, right? I heard 1.5, which is correct, but I'm going to do it keep it as a fraction. What's 1/2 plus 1? That's the same as 1/2 plus 2 over 2. Common denominator, which is 3/2. 3 over 2, which is 1.5. But this becomes 1 over 3/2. X to the 3/2 or u to the 3/2? U, right? It's u to the 3/2 plus a constant. And remember what I said happened here when you have 1 over a fraction? What happens to it? It flips, right? So this really becomes 2/3. Any questions on how I got this? I'm going from last class, well, a couple of classes ago when we did power rule. All right, so the next line will be 1/3 times 2/3 u to the 3/2 plus c. So I went ahead and flipped that fraction. What's 1/3 times 2/3? Straight across. 2/9. And let's go ahead and replace u. What is u? The 3x plus 5. So we're going to have 2/9. Watch how I write this. 3x plus 5 raised to the 3/2 plus c. Wow, that's weird looking, huh? I'm going to write the answer down here again. 2/9, 3x plus 5 to the 3/2 plus c. I don't believe that that's the correct answer. I don't believe it is. So let's check it. How would I check it? Take its derivative, right? If I asked you to take the derivative of this, you would take the derivative of the constant and it would go away, wouldn't it? Okay. So you have to take derivative of this big ugly thing, which is something to a power. So you bring the power out front first, right? So let's do that. I have a 2/9 sitting out there. I bring that 3/2 out. And then I rewrite 3x plus 5. And I subtract 1 from this. If you subtract 1 from 3/2, you get 1/2. Times the derivative of what's inside, right? We have to take derivative of what's in here, which is 3. Y'all agree? Yeah. Okay, when this is all said and done, we should get this. Let's see. The 2's cancel. Look at this 3 and that 3 together are 9, aren't they? And that cancels with this 9. So all those numbers out there go away, and all you're left with is this to the 1/2 power, which is that. So we actually got it. We accounted for all that chain rule that happens in here. And all those numbers that pop out and do all that, we have accounted for all that. And this is the result. All right. Next table in the back there. Let's see. This one's tricky. I'm giving you a second to look at it. You ready? Gotta take a swing. 5x as your u. Is that what you're saying? Okay, let's go for it. Y'all want to try that? What's the derivative of 5x? 5, which you don't have because you're going to use 5x as your u, right? So you'll be off by a constant, but that's okay. All right, let's try it. So let's try 5x here. The derivative of that is 5, so that becomes 5 dx. Any questions there? Pay close attention to this problem. We might actually run into our first problem here, our first trouble. All right, I'm going to replace this 5x with u. Yes? So that's okay? I'm going to replace dx with, well, I've got to solve this, don't I? Got to get rid of that 5? Yes? So I'm going to replace, that will become 1/5. du is dx. So now I've got it, right? So I'll be able to replace this piece. Anybody see an issue that we're going to run into? What's the issue we're going to run into? This is going to be u, right? This is going to be 1/5 du. So this is in terms of u, and this is in terms of u. But we still have here e to the negative x squared. And what am I going to replace that with? Because I don't have anything that has to do with x squared anywhere here, right? Do you see that? This has not happened. This is what I'm saying. Don't write this down. If I tried this right now, I'd have this. And this is not rewritten in terms of u only, because I still have this up here.
Would you break out the negative x squared and change it to a positive over 5x? No.
Not quite sure what you meant
No.
there.
She was trying to say you're
What, drop it?
Yeah.
Like drop it as a positive power. Even if we did put it on the bottom, we'd still have an x squared, right? So we still haven't taken care of that. So this is a good example. I'm glad we did this one. This is an example where you take a swing and you realize that, you know what, my substitution, what I picked, things are not working out nicely and cleanly like they have been, which means I need to step back up to the plate and take another swing with something else, okay? I always tell my Cal 2 students, you need to be prepared to fail more times than you succeed when you do these problems. You have to learn to make the mistake, and then over time you get better with it. Okay, so we're going to start over. All right? And we're going to try and see if we can maybe see a different u. All right. I'm going to give the same table an opportunity to try a different u. You want to go with the whole negative x squared? Okay, if you take the whole negative x squared, what's the derivative of that going to be? Well, let's write it down because it might be hard to keep track of in your head. Negative x squared is going to be what you're going to pick for your u. The derivative of that is what? Negative 2x. And if I multiply both sides by dx, I get negative 2x dx. Do you have a negative 2x dx there? Do you have this there? Almost. Everyone pay attention to this. Let me rewrite the original problem. I just moved that 5x that was in front of the e to the negative x squared. I just moved it to the back, right? We have a negative 2x dx. What appears in the problem is a 5x dx. We are off by a constant, right? This one has a 5, that one has a negative 2. That's still just off by a number, right? Yes? That's okay. That is okay. So what I'm going to do here is I'm going to try and see what I can get to match up. Coming back over here, this negative x squared will be replaced, right? That's good. We're going to take care of that. That's going to be a u, right? But in terms of this piece matching up with this piece, we know we can't match it up exactly. So here's what I'm going to do. The x dx, that they both have, right? They both have an x dx. Agreed? So let's solve this for x dx. How would I get the x dx by itself here? How could I get rid of the negative 2 that's in front? Multiply both sides by negative 1/2. So I'm going to multiply the left side by negative 1/2. And then the right side will just become x dx. And I'm going to see that I have my exact replacement right there. So let's see. See what happens here. What the hell? Okay, integral. This is going to become what? E to the u. Now, the 5, I never even messed with the 5, did I? The 5 is just going to come down. 5. Now, x dx gets replaced with what? Negative 1/2 du. And that's going to be a negative 1/2. It's going to be multiplied. So I'm putting negative 1/2 du. Okay, so this right here, right, is that piece right there. So would you agree with me that this is really negative 5/2 integral, negative 5/2 e to the u du? So this comes together to become negative 5/2. I've got e to the u and I still have du here. This is a constant. It's going to come for the ride. Antiderivative of e to the u is what? Just e to the u plus c. And the negative 5/2 will come along. So we now have negative 5/2 e to the u plus c. Last step. Replace your u with, in this case, negative x squared. Okay. That was a good one. I liked it. Let's do maybe one more, maybe two. I want to at least try and get a little around the class. I'm going to give you one that's really crazy, actually. I'm not sure the book does something like this, but this is so much fun.